Organic reactions are many kinds. As we did in the previous chapter, we learned about the fact that there are substitution, addition, elimination, and then rearrangement reactions. So given all those different kind of reactions, in this chapter, we will focus on two different kinds of reactions, substitution and elimination. And I've separated that out into two different topics. Okay, so first we will take substitution reactions only. So first of all, the kinetics, okay, of a nucleophilic reaction. We didn't talk too much about kinetics before, but I just want to mention that we need to know a little bit about what is rate law, okay, which is the order of reaction. So just a review, okay, of what kinetics is that if you have a zero order reaction, then the rate of the reaction is independent of the concentrations of the reactants, which means you can change the concentration as much as you want for the reaction, and the rate will not change, okay, or the speed of the reaction is not going to change. This is kind of what happens in case of enzymes in our body. Those are all zero order reactions. You can eat as much as you want, but your body is going to digest it only at its own pace, okay, so you're not changing the rate of reaction. A first order reaction is when the rate of reaction doubles, when one of the reactants is doubled. Okay, so if you have three starting materials in there and one of them is doubled, then the order of reaction is also doubled, which means that the rate of reaction is doubled. If you have only one starting material and even that is doubled and then the rate changes, that is also first order. Second order of reaction is when the reaction rate quadruples, okay, when two of the reactants are doubled. The two of the reactants may be the same reactant or maybe two different one, okay, so it depends which one we are talking about. All of these things, by the way, the zero, first, second, third, whatever order of reaction might be, is determined only by experimentation. There is no way you can look at a reaction. Well, eventually you'll be able to predict, but otherwise there is no way you can look at a reaction and say it is going to be first order or second order. So these reactions, they actually have to be worked out in the lab, and then you study them and then figure out what is the order of reaction, okay? But why do we need to know those? Okay, why do we need to know the order of reaction? And we need to know this because it helps us to understand how the reaction is working. Most of us have not really quite thought about how a reaction works, okay? But this is a very important part of any chemistry, whether it's inorganic or organic. You really need to understand how a reaction works. What bond is breaking, what is forming, at what speed, can you do anything to change it? All of those kind of things help you control the reaction a little bit more. In case of nucleophilic substitution reactions, you have two species. Okay, well actually there are four species in any kind of a reaction. You have a nucleophile, you have a substrate, you have the product, and then there is the leaving group. The leaving group is actually coming from the substrate. All right, so again, nucleophile, substrate, product, and then the leaving group. Okay, this is kind of what the four things are in any kind of a substitution reaction. So as we go on in this chapter, you should be comfortable, okay, in dealing with all of these things. We talked about what a nucleophile is, okay, in the previous chapter. A nucleophile is anything that is negatively charged. Nucleophile meaning something that loves nucleus, which is a positive, which means it itself is usually negative. It may be a neutral species also, but it has to be electron rich, okay? So a nucleophile is electron rich. And then we have the substrate, okay? In case of a substrate, you have to have a leaving group. If there is no leaving group in the substrate, then the reaction is not happening, okay? And so there has to be a leaving group. What kind of a leaving group are we talking about most of the time? It's halogens, which is X, okay? X is a representation of halogens in organic, but we will have more leaving groups also later on. For this chapter, we will probably have more of halogens than any other leaving group. So we have to have a leaving group which is coming in the substrate. Then your product will have the substrate and the nucleophile, because here's what the nucleophile has done. It has come in and kicked off the leaving group, which the leaving group now is by itself, the poor thing, and the nucleophile is joined with the substrate. Okay, so this is what a nucleophilic substitution is. And here are some examples. Okay, so for example, a hydroxide comes to methyl iodide, kicks off the iodide and takes its place. Okay, so that's a substitution. So here are a couple more examples of substitution reactions. Let's talk about a very specific kind of reaction called the SN2 reaction. Okay, so first let's break it down into what we're talking about. So the 2 here stands for second order. S means substitution. N, which is a subscript, is nucleophilic. Okay, so which means we're talking about a substitution that is nucleophilic and it is second order. All right, so that's what an SN2 reaction means. And the second order means that it's a biomolecular, okay, reaction, in which case both the nucleophile and substrate are in the mechanism, okay, of the reaction. We will talk about the stereochemistry later on a little bit, but this is kind of what I want to focus on right now, okay, as to how this mechanism actually arises. So let's focus on this one reaction, okay, over here with methyl chloride treated with hydroxide to give methanol and chloride. So let's break it down first. This is our substrate. Here's the nucleophile. Here are the conditions of the reaction. And in the conditions of the reaction, you can write the 60 degrees and water on the same side of the arrow or on top of each other. It doesn't really matter, but this gives you the conditions that the reaction needs, and actually H2O is the solvent, okay, that you need for the reaction. We will talk about solvents later. This is the product that's formed, and then here is the leaving group. All right, the nucleophile kicked off the leaving group, which is right over here. This table must be familiar to you from Gen Chem 2. In your kinetics chapter, okay, you would have done these kind of tables where you figure out the order of reaction, where you keep one of the reactants constant and you change the concentration of the other one. Then you keep the other one constant and you change the concentration of the other reactant, okay? And then you see if there's any change in the rate of the reaction. How do you figure out if there is a change in the rate of reaction? Is by color changes or by temperature changes, things like that, okay? And so this is what this chart is about, okay? And this is exactly how it's done as in general chemistry. It's not separate from there. So in any case, let's look at this over here. So see experiment number 1 and 3, in which the substrate is kept constant, but the hydroxide concentration is doubled. And look at the rate of reaction, it also doubled. And then we kept the hydroxide constant, 1 and 1, and then doubled the substrate. And yet again, the rate of reaction doubled. All right, so which means that the rate of reaction is affected by both of these things, which means it's affected by the substrate as well as the nucleophile. So then when we write our rate equation, it is K and then concentration of the substrate and the concentration of hydroxide. The superscripts over here, which are the rate order, is going to be 1 and 1, okay, because, and it's 1 and 1 because it is increasing by 1, all right, it is getting doubled. And therefore you double this and you double the rate of reaction. So 2 and 2, that's 1, okay? The ratio is 1. So in any case, that's what this rate of reaction is telling us, is that the mechanism of the reaction is dependent both on the substrate as well as the nucleophile, okay? So once we know this, okay, that the rate of reaction is affected by both, then we can try and come up with a mechanism of the reaction. And in the mechanism of the reaction, we have to make sure that both of the species are taking part in the transition state, okay, because that is what drives the reaction. How you get to the transition state. In any kind of a rate of reaction, there is a slow step and there is a fast step. The slow step is what determines the rate of reaction. So the slow step is what is telling us that we actually have two things in there. The fast step does not tell us anything, okay, because that just gives us the product and it's not enough to see what's going on in the fast one. So the slow one is the one that determines the rate of reaction. So in this case, the slow step is where the nucleophile will attack the carbon, okay, of the substrate where the leaving group is, and then the leaving group has to go away, all right? And so this is the transition state that is formed, and this is the slow step of the reaction. Yet again, I'm saying it, all right? So this is the slow step of the reaction, and this is the transition state that is formed, which includes both the substrate and the nucleophile. Please note that the carbon here is kind of forming a bond with hydroxide and breaking a bond with chloride. You can't have 5 bonds on carbons, so that's why you don't see full bonds. Okay, over here as in lines, it's a dash line, all right, over here. And then this square brackets indicates that it's a transition state or an intermediate, and in this case, this is a transition state. And right here, this symbol indicates that this is a transition state. Okay, in some cases intermediates can be isolated, but transition states generally cannot be isolated. All right, and so this is the transition state that forms, and once this is formed, the next step is the fast step, and the fast step is where the chlorine actually leaves and the hydroxide stays with the carbon. Okay, so this is kind of what's going on here in the mechanism. Couple of things to mention over here is that this bond, the CCl bond, is a polar bond, so carbon is partially positive, which is why the hydroxide will even attack the carbon. Okay, otherwise why would it do that? And so this is what the delta positive and negative actually just show the polarity of the bond. So that's one thing I want to mention. And the other thing I want to mention is that this is a backside attack, which means that the nucleophile will attack from the opposite side of the chlorine of the leaving group. Okay, so they are directly opposite to each other. So when the leaving group goes away, the hydroxide or the nucleophile is on the opposite side, okay, which means just think of an umbrella flip. Okay, so here is an umbrella right now, and then the umbrella flips to the other side, okay, where you have the nucleophile here, and that is what we talk about. The configuration is inverted, okay, that is the important thing over here. So those are the key things in this mechanism of the reaction, all right? So the bond breaking and forming are kind of going on right here in the transition state, and this is the slow step. This is then referred to the energy diagram, okay, of this reaction. And so here is our nucleophile and our substrate. This is the transition state. This was the slow step. And then the fast step is right here where the products are formed, okay? Remember, we have the energy of activation, which is from the starting material to the transition state, okay? Over here, transition states are over here. This graph, okay, tells us that we have only one intermediate. Okay, you can have multiple curves, but in this case, we only have one high transition state, okay, or one transition state with high energy. So that's what an SN2 energy diagram is going to look like. Here are some examples of a nucleophilic substitution, and we'll just mention some of these and then we'll talk about the specifics later on, okay? I want you to note a few things, okay, over here. First of all, that this is the alkyl group, here is the leaving group. Most of our leaving groups are going to be halides, as I mentioned, chloride or bromide, okay? Then we'll have some other ones which we'll talk about later. Here is a nucleophile, and this nucleophile is negatively charged, which was hydroxide. We've dealt with this before. The way you write the mechanism out is that you will write the hydroxide attacking the carbon where the leaving group is, and you would try to do this from behind, okay? And then the leaving group leaves, okay? So here's the second arrow, and so this is your product, and then this is your leaving group right here, bromide. The sodium is the counter ion, okay, and so nothing happens to sodium, it is still there. And then here, this is an example of a neutral nucleophile. Sodium hydroxide, in this case, the hydroxide is negatively charged, and this one is a neutral nucleophile, in which case the lone pair of electrons are going to do the attacking. So here again, same thing, here's the attack, backside attack, bromine leaves, here is bromide, and now because the nitrogen is still there, now it has a positive charge because now it has 4 bonds. It had 3 to begin with here, and the 4th one that it formed just now with the carbon. All right, so you have 4 bonds on nitrogen, so it gets a formal charge of +1, which is fine because the counter ion is right there, okay, with the bromide. And so this is how it will work if you had a neutral nucleophile, but it has to be electron rich. So what are the uses of a substitution reaction? Well, there are many. Okay, so one of the most important things is that you use it for synthesis of other classes of compounds, which means other functional groups. Okay, and so literally this is a halogen exchange that's going on where you have the nucleophile and the substrate. The substrate has the halogen, that is a leaving group, and so you can form any product that you want. So here are some examples. These are any kind of alkyl halide that you take depending on what you're making. Here are the nucleophiles, and keep a note that almost all nucleophiles here are negatively charged except for this one over here, which is neutral, but otherwise they're negatively charged. And we'll talk about what makes a good nucleophile, all right? But what the nucleophile is doing here is that it is kicking off the leaving group. The leaving group in all of these cases is X minus, or the halide that's leaving away. The products that are formed is another alkyl halide in case you wanted to do a halide exchange, and alcohol, ether, thiols, amines, azides, alkynes, and nitriles and esters. These ones we will deal more in organic too, but otherwise you can make any kind of products, okay, or any kind of functional groups using SN2 reactions. So synthetically speaking, these are very useful kind of reactions, all right, which is why they're studied so much. What affects an SN2 reaction? We talked about the fact that SN2 reactions are second order reactions. If they're second order, it means that the nucleophile has something to do with it. If they're second order, it means that the substrate has something to do with it. But if you paid attention, which you probably did, is that the nucleophile is negatively charged and also the leaving group is negatively charged. So what is it that makes a nucleophile so good that it can kick off the leaving group, okay, from there? And what makes the leaving group go away then? So these are the factors that we will talk about, okay, in SN2, because you need to know what makes a nucleophile a good nucleophile so it can get rid of the leaving group. Does the size of the nucleophile have to do with anything? And then the substrate. What kind of a substrate do we need? If the substrate is not good, obviously then you'll have no reaction, okay? Because substrate is part of the rate of the reaction. The leaving group has to be good. If it's not willing to leave, then you're done, no reaction. And then finally, we have the solvent, okay? Solvent is the last thing we talk about because it does affect the rate of reaction, and for almost all reactions that we do, you need to dissolve them in something, okay, in order to do the reaction. So we have the effect of solvent in there too. Let's take the first one, okay, which is the nucleophilic strength. Since the rate of reaction is dependent on the nucleophile, if you have a strong nucleophile, it will react faster. Okay, so which means it is important for us to know what makes a nucleophile a good nucleophile. Strong bases in general are going to be strong nucleophiles. If you remember from the previous chapters where we talked about acids and bases, we talked about strength of acids and strength of bases. We talked a lot more about the strength of acid, and if you remember, if you have a strong acid, you have a weak conjugate base, and if you have a weak acid, you have a strong conjugate base. That's where I'm getting all this information from, okay? So a strong base in general is going to be a strong nucleophile, okay? But not all strong nucleophiles are basic, okay? Hope you understand that, all right? So which means in general, we can say that bases are nucleophiles, but not all nucleophiles are bases. And why is that? Because of a very small difference, okay, right over here. Bases are characterized by their ability to abstract a proton, whereas nucleophiles react with electrophiles. Okay, that is the main thing. A nucleophile is not going to go for a proton. A nucleophile is going to go for an electrophile, which is a positively charged species. So in general, okay, strong bases will be good nucleophiles because yes, they're negatively charged, and negatively charged species will go for electrophiles, positively charged things. But sometimes a nucleophile is just a nucleophile, okay? It's not a base. So this is something that we have to talk about. I will also give you a chart in class which will help you classify these things into nucleophiles and bases. There are very few bases. Otherwise, most of them actually can be directly correlated from bases to nucleophiles, okay? Except for 2 or 3 bases that cannot really act as nucleophiles, okay, and so on. So how do we know that a nucleophile is a good nucleophile? First of all, the charge, all right? So if you have a conjugate acid-base pair, the anion is going to be stronger, all right? So for example, hydroxide versus water, hydroxide will be stronger than water. Amide, which is the conjugate base of ammonia, the amide will be the stronger base, okay, in case of these two. Regarding hydroxide and amide, how do you decide between hydroxide and amide? You really have to go back to the acid-base chapter and look into how to figure out which acid is stronger or weaker, and then determine which base is going to be stronger or weaker, okay? But right now, in this case, we're talking only about the acid-base pair. Periodicity, in this case, we use the periodic table, and if you have a more electronegative element, then it is going to want to keep its negative and not give its negative, all right? So fluoride, for example, will make a very poor nucleophile because it's highly electronegative. It's on the right-hand side. Hydroxide will make a better nucleophile than fluoride, all right? And similarly, ammonia makes for a better nucleophile than water, all right? Remember, what is the negative species here? Nitrogen versus oxygen, okay? And so ammonia is then a better nucleophile than water is. And then the size, okay? That's the last thing here. In nucleophile strength, and the size increases as you go from top to bottom, and iodide is a better nucleophile than bromide or chloride, all right? So iodide is very electron rich, it's huge, it's a huge atom, okay, very, very negative, and so therefore it becomes a really good nucleophile. One of the things about the iodide is that it's a little bit contradictory because iodide is also a good leaving group. Okay, why is it a good leaving group? Well, we'll talk about that. Okay, so once we get there, I'll mention this again to you. All right, so it's a little bit contradictory, but bromides and chlorides really make for excellent leaving groups. Okay, which is why you see them all the time here. Here are some examples of nucleophiles. You may want to keep this chart handy in the beginning, and later on you will get used to it. So here are the strong nucleophiles, okay, that you need. See, all of these are negative, 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 negative. Okay, some of the neutral ones are the phosphorus and the nitrogens, okay, because they make for really good nucleophile. Remember this phosphide here would be better than the amine, okay, because this is larger than amine, all right? The sulfide here, the SH minus, is better than hydroxide, again, because the sulfur is bigger in size than hydroxide, okay? So this is better. So here are your strong nucleophiles. The moderate ones are over here, which means they're okay, they're not too bad. When you're thinking about moderate nucleophiles and you have to wonder if the reaction is taking place or not, you really have to look at the leaving group also, okay? And then here are the weak nucleophiles. For a weak nucleophile, you really need to have a really, really good leaving group, okay? Otherwise, the nucleophile cannot do its work. So fluoride, as we just said, not a very good one. Water, methanol, alcohols in general, they're not very good because they're not charged and they're highly electronegative. So these don't really make for very good nucleophiles. So the size of nucleophile, one of the things that we talked about in the size of nucleophile was going down the periodic table. In this case, we're talking about a little bit different kind of size, okay? And the size that we mentioned over here is actually for alkoxides, okay? Alkoxides, which are alk, that is any kind of an alkane, and then an oxide, just like you have hydroxide, which is OH minus. In this case, it's alkoxide instead of hydroxide. And so in this case, you can have any kind of an alkoxide. And so the smaller nucleophile, an ethyl oxide will be better than T-butyl oxide because T-butyl is really bulky. And you have to think about why that is true. And it is true because in SN2, the attack is happening from the backside. Okay, and so the nucleophile has to access the carbon, okay, that has the leaving group on it. If it's not able to access that carbon, then it cannot do the reaction. So if you have large nucleophiles, they will not be able to access that carbon. So smaller nucleophiles like an ethyl group will be better than the T-butyl group because these ones cannot access the carbon. Okay, so just a little bit about alkoxides. I don't want to forget this part over here, is that alkoxides are really good nucleophiles and you will see them all the time. Okay, and usually these alkoxides are made as salts, potassium or sodium. And the best way to make them is by dissolving sodium in that alcohol, whatever alcohol, if it is methanol, ethanol, tertiary butanol, whatever it is, you take the alcohol, dissolve the metal in it just as it is, neat. Okay, it's a very vigorous reaction. And then you end up getting the alkoxide. Okay, of course, you also get hydrogen in the process where this hydrogen is going away. This is a very water sensitive reaction, okay, because this is a strong nucleophile, which means negatively charged. If there is any water present, it will abstract the proton from the water. Okay, so this has to be protected from water and it has to be kept oxygen free because oxygen and hydrogen do not make for a very good combo. Okay, and so this has to be done very carefully. And as soon as you make the alkoxide, you have to use it up. If you don't use it up right away, you will lose it. Okay, and so it's an instantaneous thing. You have to make it and use it. Sometimes they're generated in situ. In situ meaning that you generate the alkoxide and then you add the substrate right there, okay, in it. A little bit about nomenclature. A small one, nucleophile coming from methanol is sodium ethoxide. From ethanol, it will be ethoxide, okay, and then T-butoxide. You always have to name the metal first, sodium ethoxide, potassium ethoxide, and so on and so forth. Now let's look at the substrate and how it affects the rate of reaction or the SN2 reaction. So here, remember steric hindrance, okay, back from conformations and all that. So steric hindrance is when you have bulky groups occupying a space, all right? So in case of SN2 reaction, our reaction is where the nucleophile actually comes from the backside. And when it's coming from the backside, it has to be able to access the carbon that has the leaving group. If the nucleophile cannot access this carbon or the electrophile, then the reaction is not going to take place. All right. So for example, look at this nucleophile here, okay, or substrate. Look at the substrate here, which is ethyl bromide. In case of ethyl bromide, there is a CH3 group here and two hydrogens. Here is the hydroxide attacking the carbon, okay? Not too bad. Here comes isopropyl bromide, which is a secondary bromide, and here is the carbon. Now you have two methyl groups and only one hydrogen. It's getting a little bit harder, but hydroxide is a small base, so it can access. And then we get to T-butyl bromide, okay, which is a tertiary bromide. So you have three methyl groups attached to the carbon, which has the leaving group. And now this is too crowded. Okay, so the hydroxide now cannot really approach the carbon, so which means that this reaction is not going to happen. All right, so this is a nice visual of a space-filled model to show these things, where you have ethyl bromide, isopropyl bromide getting a little bit cluttered, steric hindrance, and then with the T-butyl bromide, okay, completely inaccessible carbon. All right, and so in general, we say a primary substrate is better than secondary, and that's better than tertiary. Okay, that's how it goes. Here again, same thing. Okay, just gives you a good idea about how this works. This is the reactivity of the different kinds of substrates that we have. So a methyl bromide, for example, okay, it reacts so much faster than a primary, then a secondary, and then look at the neopentyl. Okay, it just gave up. And tertiary, forget about it. It's not happening. Okay, and so steric hindrance plays a big role in the reactivity of SN2 reactions. Leaving group. Now, leaving group is the opposite, okay, of a nucleophile. A nucleophile is attacking the carbon, whereas the leaving group is leaving, okay, the carbon. Both are negatively charged species, okay. So what makes a good leaving group a good leaving group? And that usually is going to be a weak base. Okay, a weak base makes a good leaving group. Remember, a nucleophile has to be a strong base, so the leaving group has to be a weak base. Okay, so it can go away. Only something stronger can kick off something that is weaker, all right? So a strong nucleophile will kick off the leaving group from the electrophile. Otherwise, it's not leaving, all right? So if it's not going to be stable, then what's the point, all right? So a leaving group, a weak base is going to be stable. And that is the driving force also of this reaction, is that if you have a good leaving group, then the reaction will take place. Okay, so here are some examples, okay, of the leaving groups. And once you look at these ones, you will see how they make for good leaving groups. Now, this is a little bit of a controversial thing, right? With the iodide, okay, as I mentioned to you, because iodide is a good leaving group, but it's also a good nucleophile. It's a good leaving group because iodide is the conjugate base of a strong acid. HI is a very strong acid, if you remember from the acid-base chapter. So if it's a strong acid, then its conjugate base must be a weak base. So if it's a weak base, then it's a good leaving group. On the other hand, iodide is also a very good nucleophile because it's so huge and it's negatively charged. Okay, so this was the controversy that I was mentioning about iodide. So look at all of these, and these are all conjugate bases of strong acids. Okay, sulfonate, sulfate, phosphate. So this is coming from phosphoric acid, sulfuric acid. Those are strong acids. So conjugate bases of all of the strong acids will make for good leaving group. The conjugate acid for Cl minus is actually HCl, okay, hydrochloric acid. And so it makes for a very good leaving group because the conjugate base of a strong acid is weak, okay. Some of the neutral molecules are like water and alcohols, amines. Now these ones here again, you might think a little bit controversial, okay, but then it depends on the nucleophile that is attacking. So if the nucleophile is good, then it can get rid of the amine and the phosphines also. Water is an excellent leaving group, okay, because water is a very weak base, okay, and so are alcohols. They make for really good leaving groups. Here are some numbers for you, okay, and tosylate, which is something like this, okay, over here. A tosylate makes for a really good leaving group, and this is going to be important for us when we get to the alcohols chapter. In this chapter, we don't deal with it so much, okay? But later on, you will deal with tosylates. So this makes for a really good leaving group because it comes from a very strong acid. Then iodide, really great leaving group, okay? And then so on and so forth over here. By the time you get to hydroxide and amide, remember these were actually very good nucleophiles. These are going to be terrible, terrible leaving groups. Okay, so if you have any of these ones in your substrate, well, that substrate is not going to do any reaction, okay, at all. So how do you promote your reaction? By having a super duper leaving group, okay, like this, a weak base. And then finally, solvents, okay. A solvent, the purpose of a solvent is to not react with any of the substrates or the nucleophiles. So it should be unreactive. The other thing is that it should support the reaction. If it doesn't support the reaction, then why is it even there? Okay, and so those are the two purposes, okay, of any kind of a solvent, is to support the reaction and then of course not take part in the reaction itself. There are three kinds of solvents that we deal with in organic chemistry: polar protic, polar aprotic, and nonpolar. Polar protic, protic meaning something that has a proton. So which means that anything that has acidic proton like water and alcohols, those are considered to be polar protic solvents. And if you have an acidic proton, obviously then you have a polar bond, okay, which is what makes these solvents polar as well as protic. So these are polar protic solvents. But polar protic solvents create a problem for us because if you're dealing with strong bases, then you can have a reaction with these acids, okay? And so for that reason, we have another class of solvents which are called the polar aprotic solvents. In polar aprotic solvents, we have something that doesn't have the acidic proton anymore, okay? So it's the DMF, DMSO, dimethylformamide, and dimethyl sulfoxides. These are very good polar solvents, but they're aprotic, so they don't provide for the acidic proton. Here is the structure for dimethylformamide, DMF, and then DMSO is this one. Okay, so they provide for the polarity, which is coming from the sulfur oxygen, and here in the carbon and oxygen, carbon nitrogen. So they are very polar solvents, which means that they have really high boiling points and all, but they don't react with the substrate, okay, or the nucleophile. And then finally, we have the non-polar solvents. In the case of non-polar, all the bonds are non-polar, okay, so pretty much all the alkanes, some aromatics, okay, some ethers, these are all considered to be the non-polar solvents. Okay, so which one is good for SN2 reaction? With SN2 reaction, you need to have something that supports the transition state, okay, and the transition state here is for SN2, okay. And so the polar aprotic solvents are considered to be the best for the SN2 types of reactions, okay, because they help to stabilize the transition state. The non-polar are not very good because they don't stabilize the transition state. How? Because in the transition state, there is a charge dispersion, okay, going on. So if you have a charge dispersion like delta negative, delta positive, you need to have a polar solvent in there. If you have a polar protic solvent, then that will start reacting with your nucleophile. So you cannot have a polar protic solvent. So polar aprotic solvents are best to support SN2 reactions. What this means is that if you try and do an SN2 reaction in hexane, then the reaction is either going to go very slow or it's not going to even occur. Okay, so that's what it means that when you have a good supporting solvent in there. So for SN2, polar aprotic solvent. One little review yet again for stereochemistry of SN2 reactions, and I just want to emphasize that you understand the whole flip thing that goes on, okay? Because the nucleophile is attacking from the back side of the leaving group, the whole molecule flips onto the other side. And once there's inversion of that side, then there is inversion of configuration. Okay, so this whole flipping thing causes for inversion of stereochemistry. And so if you start with an enantiomer which is R, you will end up with an enantiomer that is S because everything is now flipped, okay, on the other side. So here's an example, and then in a cyclic compound, it's a little bit easier to see because here you're starting with a cis compound where both the hydrogens are on the same side, and then here's your leaving group. So if the hydroxide comes from the back side and attacks over here, then your hydrogen will move to the other side to compensate, and the hydroxide comes and attaches here on the back side. And so you end up with trans product. Okay, you started with the cis starting material and your product is trans. So again, we have inversion of stereochemistry. So in case of straight chain compounds, you have R and S going on. And in case of cyclic compounds, there is still R and S, but it's easier to see the cis and the trans going on. That cis and trans change going on for cyclic compounds. All right, so the stereochemistry is inversed in SN2 reactions. Let's look at a different kind of reaction now, and that is called an SN1 reaction. So again, substitution, nucleophilic, but this time it is a first order. Okay, so we just finished SN2. Now we are talking about SN1. First order unimolecular reaction then. So in the previous one, since in SN2 we had a bimolecular, it means there were two things that were involved in the transition state. Here the first order indicates that we have only one thing involved in the transition state. So which means we have to figure out whether it is the substrate or the nucleophile. Okay, that is affecting the rate of reaction. So we'll do that in the next slide. In any case, one of the properties of SN1 is racemization, which we will talk about, okay, later. Let's look at the mechanism of how SN1 works. Okay, so here's our substrate, here's the nucleophile, here is the product, and here is our leaving group. Okay, before we even look at the mechanism of this, I want you to focus on the reaction for a minute and look at the substrate. Okay, the substrate is very different from what we had before, which was a primary halide, okay, which was methyl chloride or methyl bromide. So it was a primary halide. Now we're looking at a very sterically hindered halide, okay, tertiary carbon over here. And our nucleophile here, the 2H2O, this is not even a nucleophile, right? Because according to our SN2 reactions, our nucleophiles were negatively charged, fairly good bases, okay? Whereas water is not really a very good base. So right away you can tell that an SN1 reaction is very different from an SN2 reaction, okay? The kinetics of this reaction shows that it is a first order reaction, all right? And once you do more deeper kinetics of rate of reactions, it turns out that the mechanism is independent of, or the rate of reaction is independent of the nucleophile, which means that the rate of reaction is dependent only on the substrate. So remember the chart that I was showing you before where you change the concentrations and then you see what happens to the rate of reaction if you change either the concentration of substrate or the nucleophile. Well, here, if you change the concentration of the substrate, if you double the concentration of the substrate, then the rate of reaction doubles. If you change the concentration of the nucleophile, nothing happens, which means that the entire reaction is dependent only on the substrate, which means that our mechanism and our transition state, the rate determining step, that is all dependent on the substrate. Okay, so now we can start looking at the mechanism of the reaction. If we are only dependent on the substrate, then we'll start with the substrate. Okay, and this is our substrate where we have T-butyl chloride, and the slow step, the rate determining step, is where the chlorine leaves. Once it leaves, here is the leaving group already. And here we have a carbocation, okay, which is a positively charged carbon. We did not see this species at all in SN2 because it did not exist in SN2 reactions. It exists only in SN1, okay. So here we form what is called a carbocation, 3 bonds, okay. I want you to note one more thing while I'm here, we'll mention it again, is that carbon went from being tetrahedral, sp3, to being trigonal planar, which is sp2. Okay, that's an important part of this mechanism. The second part is where the water comes in. Water is our weak nucleophile over here. It comes in, it attacks the carbon, and remember it's the oxygen that has the electrons. It will attack the positive center, the electrophile, and then this is the species that you end up getting. Now remember, don't let go of anything until you're absolutely ready, okay, for it. So the 2 hydrogens are still there for water, and then see there was 2 molecules of water over here. So then the second molecule of water comes, deprotonates this water, okay, and so now you just have the alcohol left, and here comes the second molecule, okay, of water. So that's what the whole mechanism is about, okay. And so here is your nucleophile reacting, but our nucleophile is not quite done here until the second molecule comes in and takes away the extra proton, okay, because remember your product cannot be charged, all right, no positives, no negatives, it has to be neutral. And then here are the energy diagrams, okay, for this. The transition state for the first one, the slowest one, is the highest, okay, because that takes the longest to make. And then as this transition state develops, that's the second one, now it's getting lower in energy. And then the last one where the deprotonation occurs is this one, okay. The last reaction is really very fast then, all right. So here's the energies for all of these different transition states. And here's a little bit of a better view of the transition state. The first transition state is the critical one, okay, because the first transition state is the one that gives you the carbocation, all right. So once the carbocation is formed, the next part, okay, is where the nucleophile comes in. Now, depending on what your nucleophile is, you may actually have just 2 bumps, or if you have solvolysis like what we had just now in case of water, or here in this case of methanol as showing in this graph, then you can have 3 graphs, okay, or 3 curves over here. The third curve comes from the fact that this has to get deprotonated, okay, the oxygen has to get deprotonated. That's where the third one is coming from. If you had a negative nucleophile, then the reaction will stop right here, okay. So anyhow, this is the energy diagram. So again, remember, you can have either 2 curves or 3, depending on what is reacting. But the main point is it is different from SN2 reaction, if you remember, because SN2 had only 1 curve. And why 1 curve? Because there was only 1 transition state. In SN1, you have 2 or 3 because there are 2 or 3 transition states. Let's look at the stereochemistry of SN1 reaction, because as I mentioned to you before, the racemization occurs. So let's look at it a little bit deeper. Okay, so let's say that we start with something of an S stereoisomer. Okay, and so this is a tertiary carbon. if this bromine leaves away, then you end up getting a carbocation. So here the hybridization on this carbon went from being sp3 to sp2, and sp2s are trigonal planar. So here is a trigonal planar intermediate carbocation. And if you have a trigonal planar carbocation, then the nucleophile that has to come can come from either side. Okay, it can come from the top or it can come from the bottom. Okay, and so if it comes from the top, you end up getting one stereoisomer, and if it comes from the bottom, then you get the enantiomer. Okay, and so both the things can happen in this case. All right, so you have inversion going on, so S giving you R, and then S giving you the same one, depending on where the nucleophile is attacking from. So you get inversion and retention, okay, of stereochemistry. Now, when we say racemization means that you end up getting a racemic mixture, which means an equal amount of S and R. If it is a true SN1 reaction, okay, if it's a true SN1 mechanism, then your mixture is going to be a racemic mixture, 50% S, 50% R. What do I mean by a true SN1 reaction? Sometimes mechanisms compete with each other. We will talk about that. And so once they're competing, then you can have a little bit more of one or the other, which we call an enantiomeric excess then. But otherwise, you will have an equal mixture of R and S. Okay, so a racemic mixture. What are the factors that affect SN1 reaction? If you look here, the factors are the same as SN2 reaction. So this one will go a little faster. We still have the substrate, we still have leaving group, nucleophile, and the solvent, okay, that affects the SN1 reactions. So the nature of the substrate, okay, first of all. Now, in this case, since your intermediate that is being formed is a carbocation, the carbocation has to be stable. If it is not stable, it's not going to exist, all right? And the most stable carbocation is a tertiary carbocation, followed by secondary and then primary. And methyl halide, forget about it. It's not happening, okay? And so for the tertiary, okay, that is the most preferred type of a substrate for this. Why is it more stable? And that has to do with the inductive effect. Okay, so let's see over here where we have the carbocation stability chart. In the tertiary carbocation, you have 3 methyl groups, all of which are stabilizing the carbocation. Alkyl groups are considered to be electron donating groups, and so there is an inductive effect going on. And because of this electron donation, this carbocation is stabilized, which does not happen in the methyl cation because hydrogens are not electron rich, so they cannot give any electrons. And therefore, the methyl carbocation is not stabilized. So tertiary carbocation is quite stabilized, followed by secondary, the benzylic and the allylic. Okay, these two over here are before the primary carbocation, and these two are stabilized by resonance. Okay, and we've talked about those before. As far as the benzylic resonance is concerned, you will do more of this when we get to organic 2, when we do aromatic compounds. But the double bonds here are actually involved in the resonance. Okay, and once something is resonance stabilized, you know that it will be a stable intermediate. Okay, and here also the same thing. These electrons can move over here, carbocation comes over here. So these are resonance stabilized structures, both of these. Okay, and in some cases, the allylic cation can be almost as stable as a tertiary carbocation. So that is the nature of substrate, which means that if you have more of a tertiary carbocation-like substrate, then your mechanism will be more SN1 type mechanism. The leaving group. The leaving group is a key, okay, in forming the carbocation, but as in SN2 reactions, your leaving group has to be a weak base. If it's not a weak base, it's not leaving. It is as simple as that. But your leaving group does have to leave in order for the carbocation to form. So it's good to have a good leaving group, which means it's good to have a weak base. And remember, we talked about tosylates being very good leaving group, and that is still the case. All right, so tosylates are good leaving groups. Halides are also good leaving groups. Okay, in case of OH, which means an alcohol, water becomes a good leaving group, all right, in that case. And we will do some mechanisms of water as a leaving group also. Remember, between hydroxide and water, water is a better leaving group or a weaker base, okay, hence a good leaving group. The nucleophile here, it doesn't really matter what the nucleophile is because the nucleophile is not part of the mechanism. So a nucleophile can be a strong nucleophile or a weak one. It doesn't really matter. Of course, if it's a weak nucleophile, then you will probably have a little less product. If it's a good nucleophile, you will still get a better product. But very honestly, the nucleophile does not do anything to the rate of reaction, so it is not the most important thing for SN1 reactions. And then the solvent. Okay, so now the solvent has to be a polar solvent because it helps with the ionization, all right, of the carbocation. Carbocation is a cation, okay, which means that it is an ion. And ions are stabilized only in polar solvents. They are not stabilized in non-polar solvents. So if you have a nice polar protic solvent, then it's a nice stabilized reaction, okay? And polar protic solvents are good over here because they also provide for hydrogen bonding, okay, which helps with the stability of the carbocation. You can also use the polar aprotic, but polar protic solvents are better. So here is a summary of the reactions that we have done so far. We have SN1 versus SN2 kind of a reaction. So let's look at through all of these things and see what is different, okay, between both of these types of reactions. So for substrate, SN2 reactions requires a primary or a methyl. It doesn't mean that the secondary will not react. It's just that these are preferred, okay? And so your secondary will react. You will just get different kinds of products, okay, for that. SN1 will prefer a tertiary carbocation, and therefore a tertiary substrate is good for SN1 reactions. And again, so the secondary will fall kind of in the middle, okay? And it's a little dicey when it comes to secondary substrates. Nucleophile, a strong nucleophile is preferred for SN2. For SN1, a weak nucleophile is fine. It can be the solvent also, and hence the word solvolysis, okay? Because solvolysis means that the solvent is reacting. Remember, we talked about solvents in SN2 that they should not react with your carbocation or the electrophile. But in SN1, sometimes the solvent actually is what is reacting, all right? So it poses a problem, but it's something to consider. Solvent here then for SN2 reactions, you need the polar aprotic solvent. And again, you need the polar aprotic solvent is because you have an intermediate that is charged, it has partially positive and negative. So that is supported by a polar aprotic solvent. And SN1 is supported by a polar protic solvent. What I wanted to say is that SN2s, you cannot use the polar protic solvent because then the hydrogen bonding will stabilize this. And if the intermediate is stabilized, you will not get the product. The kinetics of the reactions for SN2 is dependent on substrate as well as nucleophile. So it's a second order reaction. In SN1, it is dependent only on the substrate. Stereochemistry. We have inversion of stereochemistry for SN2, and in SN1 you end up getting a racemic mixture. Okay, and the rearrangement part, we will talk about this also as time goes on. In SN2 you don't get rearrangement reactions, whereas in SN1 there is a possibility of getting a rearranged product, and we will talk about the rearrangement later on as time goes on, but I just want to throw it out there that we still have to do rearrangements. Okay, so that's the differences between SN1 and SN2 reactions. Here are some problems, okay, to think about. So predict the mechanism and stereochemistry of each product, all right, or for what happens in the reaction. So here we're starting with R2-chlorobutane. This is what the compound looks like, and here is our nucleophile. So this is a secondary halide, okay, and because this is a secondary halide, it's kind of tough to decide whether to go with SN1 or SN2. Then we look at the nucleophile and we're like, oh, where is my nucleophile? Where is my negative charge? Which means that I don't really have a very good, strong nucleophile. So which means I'll have to go with SN1 type of a reaction. And also this kind of a reaction will be called solvolysis because my solvent is going to do the reaction. And if my solvent is doing the reaction, then my product will have alcohol coming from the H2O, and then the ether group over here, OCH3, coming from the methanol, okay? And because it was an SN1 reaction, I also lost stereochemistry. Why did I have SN1 again? It is because I have a secondary halide and not a very good nucleophile. Okay, that is why I had SN1, and that's why I had solvolysis in the first reaction. In the second one over here, we have a primary halide. It's a little bit sterically hindered over here, but not too bad. And then we have Cn minus, the cyanide, and sodium cyanide. Okay, and the cyanide here is the nucleophile. So negatively charged nucleophile, okay, fairly good enough. Okay, and so this will then do an SN2 mechanism, and you'll end up getting this type of a product, okay, which is a nitrile actually. And in this case, stereochemistry is not given to us, so we don't have to worry about showing stereochemistry. Bromide is our leaving group. Here is the mechanism for R2-bromobutane. Now this substrate is similar to the first one. We had chlorine as a leaving group here, but now we have bromine as a leaving group here. And of course, our nucleophile has changed a lot. Okay, so here we have a thiol, CH3S minus. And as soon as you see a minus, you're like, okay, I got a good nucleophile. And here we have methanol in the first example that we did. So in this case, this was just a solvent, whereas here now we have actually a negatively charged nucleophile, so fairly good, okay? And so then acetone, which is a little bit of a polar solvent, and then we end up getting this product over here where bromine is leaving as bromide, and then SCH3 is attached to the bromine. Now, why is the stereochemistry not shown over here is because this is a secondary halide. Okay, and if you have a secondary halide, then you don't really have a clear-cut shot of SN1 or SN2 reaction. Most likely this will be an SN2 reaction, which means that this one should be an S enantiomer, okay, over here. So inversion of stereochemistry, I would show that. The book did not show it, okay, but I would show inversion of stereochemistry over here, okay, because we start with R, end up with S. So here are our keywords and our concepts that you need to know from this chapter or this section of this chapter. This is only half the chapter. You need to know the substitution reactions. You need to know all these different terminologies of the nucleophile, electrophile, and the leaving group, unimolecular, bimolecular, transition states, the rate determining step, not so much, okay, but the formation of the carbocation then is the important part there. The different kind of solvents that we have, and this term called solvolysis, which is when the solvent starts reacting, okay. So you need to understand all of these things. You also need to be able to understand the graphs, okay, that I posted there for you. So you need to understand what kind of an energy graph will you see for an SN1, what will you see for SN2 reactions, and then of course be able to predict products. So we will practice some of those in class, and I'll give you plenty of handouts, okay, to work on.